I will post this, but this will pretty much be what you guys want to make of it. Again, I'll discuss the overall format. I'd like to give you a little information as to what topics you should focus on, because I know that's always stressful during the finals to know what are we going to ask, because it has been a long quarter and there has been a lot of stuff. So I'm just opening a file now, but bear with me for a second. Sorry. Okay, so let's go ahead. Get started. Let me share screen. And then we'll talk about it. Okay, so unless you've been under a rock for the last few weeks, you know our final is on Monday. It's this June 7th. So that's the day we'll have our fun. So I just want to let you know. So let's talk about part one, and then we'll spend more time on part two. So part one, out of the final, there's 100 points allotted. Those will be normalized because the final counts for a fair amount of your grade. I think I put it down as 30%, 35%. I can't remember right off the top of my head what it is, but so I'll normalize those points. If you're curious how you're doing, I did finish grading the quizzes. Most of you did pretty good on them, and I posted those grades today on Canvas. So your grades percentage, that's the weighted percentage you have going into the final. That's up because all the points on Canvas are equivalent. So 20 points for homework is the same as 30 points that you get for a quiz. So I would look at that as the lowest that you have. That's without any curve, any extra credit for doing the exam wrapper. So you have that. So it can only go up from there. And so keep that in mind. Now you'll have all day, 9 to 5. I'm not sure it's going to be 9 to 6, but I didn't want to promise you now unless I knew. But I'll post that when I know for sure. We're still trying to finalize the exam, the person who's in charge of it. We've put forth all our questions. They're just compiling at this point. So you have, for that part, you have 60 minutes. If you're DRC, you'll be given additional time, just like on quizzes. And the focus of part one is conceptual short calculation questions. So multiple choice fill in being you'll answer a question. So I might have like a simple friction question. You calculate a force required to move something. You might have a moment about a line, and you might have to calculate the unit vector, or you might have to calculate the R vector, just stuff like that. So the only downside to it is no partial credit because it's graded in Canvas. So we're pretty careful about how we set it up so there's no mistakes. I would say is that if in the multiple choice, we try to say choose the best answer. So if you think that none of the answers are perfect, that's fine. Just choose the best one in your opinion. And so I would be familiar with free body diagrams. I know it's something I've been harping on all quarter. Overall, I don't think free body diagrams were where they should have been with some of you. Given the small sample size it's here, it's probably not the ones that are listening to this, but the ones that haven't been. But I would say that you really need to, if you're still not sure about them, it's something you really need to focus on because it is going to come back in 204. It is going to come back in dynamics. And so I think most of you are probably in line to take those courses. All right, so then that's the part one. So any time of day you want to take it, you can take it. I will be around most of the day. I would send, if you have a question, send me a email. I can't promise you I'm going to be able to answer it. I don't have office hours that day because it's finals. So just make your assumption on it and go from there. So, all right. That's part one. Any questions on part one? Okay, so part one will come from all the topics, and I'll go over those shortly. But so anything we've talked about in the quarter from a conceptual standpoint is fair game for this part. All right. Now, part two, that's going to be taken live with Zoom in a Zoom room, the same one you're in now, and we'll enjoy each other's company from 7:10 to 8:40 p.m. on Monday. And the way to approach that is there'll be 2 or 3 midterm type questions. There won't be 4, or there won't be 1. There'll either be 2 or 3. And so you have actually an hour and a half to do what amounts to probably the same or less work than you have in the midterm. So everyone's getting a little extra time here, which I think will be beneficial for you. If time was an issue on the midterm, then this is good because you'll be able to take your time, really concentrate on things. So topics now, and this is the important part of the topics, are 3D equilibrium, moments, centroids, moment of inertia, trusses, frames, machines, and friction. So what I would say is that if you're thinking about studying, these are what I'd call the 6 major categories that we always test out of. So let's break those down a little further. So 3D equilibrium, you may recall that's end of chapter 4 stuff. So 3D equilibrium, 2D equilibrium, solved the same way, moments about a point, sum of the forces in the X and the Y. We usually don't test on 2D equilibrium because it's pretty easy, and you should know that. And so the 3D equilibrium, as you saw in the exam, those in the midterm, those questions can be a little longer, a little more involved because you have to identify your R vectors, you need to identify your reactions, you need to identify your direction of your forces, and then ultimately set up your moment equation. So if we give you one of those on for the midterm part 2, then most likely you'll be given some information. What I mean by that is you might be given all the R values, you might be given, or you may only be asked to set them up. And I really want to emphasize this, and this is important. If you set up a 3D equilibrium, it's not enough to just write R cross force at AB, R cross force at AC, and so forth equals 0. That is the governing equation, yes, but you can't. And let me go to my dot cam because I want to really want you guys to have no question on this. Do this. So let me just try to get this to focus. Let me try to write something so it has something to grab hold of. Okay. So let's say for example, you had a question where you had hinges here, and you had some force on the door, and you were asked to find, let's say this is A and this is B. You're told to find reaction at A. All right. So let's say you're asked to do that. So you remember from before is what you're going to have to figure out is what are all the forces acting at on A, and you're going to set up moments for that. So let's say that in your free body diagram, we're given, we just isolate the door. That's all we care about. And so we have our, we're going to assume in this case that here's our axis. We'll make it easy to make this the axis. It's a little different than that. But so we know we have a force here, and we'll have a force going like that. So make this our, and so we'll call that AX and AZ. That'll be from here, and the same thing down here. We'll have B, Z, and say B, X. Okay, so what I did is I just put my 2 points here. Maybe it's easier if I draw the X. All right, try to get this moving. So then say you might have a weight, right? You may have a weight. You have a force coming out here. You know, say that's tension vector, you know, whatever it is, CD, whatever you want to call it. And so what you're going to do then is, you know, this, and there might be something else on it. The important part, and maybe there's, you know, even I think on the midterm, there's even like a force in the handle, say it's going that way. But whatever it is, whatever's present, call that point C, and this down here is D. And that's something I'm kind of reiterating what the midterm was, but because what I saw in this was, and I've seen this in the past, is where you say, okay, I'm going to take a moment about A, and this set equal to 0. Well, that's great. That's a great equation, but you need something beyond that, right? So you need R. If you're doing about A, it's going to be B relative to A. And this within it, even you may have forgotten, but this is something that can come up in a conceptual question. It could ask you, the conceptual question could ask you, what is the R vector? Does it go from the point of the moment, or does it go to the force? And so, you know, you don't want to miss that by saying it wrong. So you just want to remember it always goes to where you're taking the moment from. So if I have my moment about A, then I'm going to go from A to the force. And that's why I write B relative to A. It means it's going from A to B. And then we do the same thing with the other members. So if R, A, B relative to A, and then we're crossed with whatever's at B. So we just draw B as a vector and so forth. And then we just do the same thing with R. So R, C relative to A, crossed with whatever tension CD is, and then plus R, we call it G relative to A, crossed with the weight, and then plus R, E, and we'll call this point E, and then be E relative to A, crossed with whatever E is. And that'll equal 0. So yeah, this is your governing equation, true, but you have to show what these vectors, you have to populate these. So you have to put in the respective components for all of them, set equal to 0. So once you have that, that would be your answer. Okay, that part there. Now, we probably won't ask you to do the cross product because we know you can do that. That's the easy part. Once you got to this, you're pretty much good to go. So, any questions on this? Anything at all? Sorry about that. I had to do something with the bird. All right. So get someone else in. All right. So that's what I was talking about, though. Let's go back to this. So 3D equilibrium. So it kind of shows you, what the expectation would be. And I think, no matter how intimidating the picture looks like, they're all done essentially the same way with this. You have, and so I'm assuming now you can see the PowerPoint, right? Is that correct? Yeah, okay. So then the next one's moments, point, line, equivalent couples, and then centroids, trusses, frames of machines, and friction. All right, so I want to go through each of those briefly, really quickly, and then I'll open it to comments. I don't want to just sit here and rattle at you. I want to give you as much information. So what I would say, let's go ahead and go back to the camera. What I would say is that you have, you had chapter 2 that you started with. So that's pretty much inclusive of other chapters. So unless you're still having trouble with vectors, I wouldn't go back to chapter 2. I wouldn't do problems from chapter 2. I think you need to, I wrote 2 there. What I would definitely make sure, and this could be something in the conceptual part, is make sure that if you have, say there's a pole, and let's say I give you, there's a wire and there's connected to, be sure that you can write the vector for this. So if this was A and this was B and you're given the coordinates, let's say you're given the coordinates of this. This is, maybe this is minus 5, 0, 8, and perhaps this is 0, 10, 0, right? So be sure that if you have these coordinates that you can then say, let's say that it's a tension vector. So we always know it's always going away from the pole. So if you want to know that what tension AB is, it's going to be equal to whatever the scalar AB is times the unit vector AB, right? So, and that this lambda AB, of course, is going to be your R B minus RA components, right? And then over the absolute value. All right. So that's a very easy conceptual problem. You wouldn't have gotten this far in the class if you couldn't do it. So, but don't hurry through it if you see one of those on the part 1, because it's easy points, and if you understand it, we're not trying to trick you on the test. We just want to make sure that you understand the fundamentals. And so, as I said, we're not going to throw any real curveballs at you guys. That's not my style. I don't teach like that. I like to give you things that are pretty mainstream to the material. And I know that your goal in this class is not to become statics experts and know every nuance of statics there ever was or is. And so I want to make sure, though, that you have the competency to move on and do well in your future classes. Okay, so chapter 2. So then we get into chapter 3. And if we break down chapter 3, we had moments. And we know by about a point, a line, and then we had those two, right? And so we know that moment about a point A is just equal to R cross F. And we know the moment about a line AB is going to be, that's a vector there, going to be the line AB vector, the unit vector, dotted with R cross F. Okay. Any questions on any of this? It's all ringing a bell, super clear?
I have a question.
Yes.
What's the difference between the moment about a line and the projection of a force about a line?
Well, one's a moment, one's a force.
But as far as steps to solve them, are they pretty much the same?
Yeah, when you're projecting a force on a line, you're taking a dot product of that line's direction to the force vector, and then you end up with a respective scalar of that force. And so the only difference would be if you're doing a force, it'd look like this. It would be scalar force, like along AB, would be lambda AB dotted with whatever that force vector was. Okay. And so the only difference is this is a moment, but the thing is the same. You're not going to see projected forces on the final. That's something that I do mainly because I want you to understand where this comes from. Because I think if you can do a projection of force onto a line, it's a little easier, because I think a force we can visualize easier than a moment. And I find that this, while mathematically simple for you guys to do, conceptually is rather abstract. Think of projecting a moment about a line in space. All right. So, but that's that. So then from there we have drawing a blank. Oh, we have equivalent couples. Right. So this is probably something you're not going to see on the test. Force couple systems, probably not. I would say that from chapter 3, this is probably what you're going to see, this less so. Okay. I mean, you should still understand force couple systems, but I mean, really, we know that if you have something like this, let's say it's a and you have force up here, and you want to know what the force couple system is down here. This is F, and this is, say, point B, and that's point A. And if we know the force is going to point C, then we just say, oh, okay, well, if we want to know the equivalent force couple at A for the C, we know it's whatever the force is, right? Whatever those are. And then we know it's a moment, and that moment is equal to R C relative to A. So you go from the point of the moment, the new moment, to the force, cross with whatever that force is. And so you want to make sure that you understand that in order to correctly answer a question like what is the equivalent force couple system, you have to include both the force and the moment. It's not enough just to include the moment. Okay, if it comes at all, but that's that. So that's chapter 3 in a nutshell. I would just make sure you're familiar with this. Don't rush through it. Don't overthink it. We're not trying to trick you if we do give you a problem like this. We just want to make sure you understand it. Now, as you may remember, is that chapter 3, we're not really in equilibrium per se. You might remember that everything here, like when we we're saying a moment about a line, moment about a point, we're not telling you what's keeping that in equilibrium. So nothing in this chapter is really set equal to 0 yet. So when you see that, don't confuse it with what you saw in chapter 4, where you're setting everything equal to 0. All right. Okay, so then we have chapter 5 and combined with chapter 9. So this will probably see on part 2 if there's a question about it, because there's not really a lot of theory you can do with it. So if it is going to be on there, it's probably going to be on part 2. And so what I would say is, you should understand that if you have some crazy shape that has a circle there, and be a jutting out pyramid, a logarithmic. No, I'm just kidding. It's not going to be that complicated. I'm just yanking your chains. So sorry. Got to have a little fun here, don't I? No, it'll be most likely if it's on the part 2, then it'd be probably a simple system. I would say it would be a rectangle, maybe a circle, or maybe not, in a triangle. And you probably break it into maybe 3 or 4 at most. So again, you don't really learn more by doing something like this. You just take up a lot more time. So we're not trying to do that to you. So in terms of turning this in, because I know a lot of you did this on Excel, then if for homework, I was thinking that how if you do want to do this on Excel, I will accept it. All right. So because I've let you do it before, because when you think the format of the way the test will transpire is part 1, you'll go ahead and you'll take it just like you take a quiz. You'll start quiz, you'll have the 60 minutes, you'll go through it, you'll submit it, done. For this part, the timer, you'll start timer, you'll download the test, just like you did on the midterm. I'll be there, you ask questions, whatnot. I'll say, all right, time to turn it in. So when you turn it in, you can upload it as an Excel file if you choose to do it that way. But again, so it's not going to be that. It's going to be, maybe something more like maybe there's a triangle here and maybe a half circle there, and that's it. So you say, I'll cut off that and cut off that. 1, 2, 3, done. All right. So for this question, you'll probably need to find X bar and Y bar. And then you'll need to find either IY prime or IX prime. So I'm not usually interested in having you do both, just one. So just make sure. But you will have to find both centroids. You'll just have to find the moment of inertia about one of the axes as asked. Now there are different versions of the exam. So some of you might be asked to find this. Some of you might be asked to find that if it's on there. It just depends. So we did make some variations. They're pretty similar though. So that way there's no, one person doesn't get the harder test, so to speak. And that's pretty much all there is with chapter 5, chapter 9. No integration, no calculus, just simple composite. All right. So then we get chapter 6, and that's where we spent probably close to 2 weeks on. And so we break this into 2. First, we have trusses. So within that, you have method of joints and method of sections. So we usually like to test you on both. So don't be surprised if there is a question on this in part 2 or even on part 1. There might be the question is, if for method of sections, method of joints, show by method of joints what member AB, BA, CD, whatever is, and for method of sections. And it'll usually be pretty obvious. I mean, if you have a truss that looks like this, right? And we want these members here. It's not going to make a lot of sense to work your way over. So, or if it's, vertical like that, maybe there's another like this and force here, force there. And so maybe you want to find it there. Maybe there's a force applied there and there. I mean, there's all kinds of variations you can do. Of course, then you might ask, what are zero force members? Of course, you know that one right away is zero force member. So you should be able to identify zero force. So that's one type of question you can see on part 2. And then the other one would be, and this can also be in these, with the exception, I would say, of this, chapter 5, 9, every other subject I'm talking about has potential to be a conceptual question because there are conceptual things we can pull out. One of the things we talked about briefly in my lectures, which you should understand, is what's called static determinant, static determinancy, or I'll say statically determinant. All right. And I talked about that in my lecture, but just real quick, I want to make sure you understand this. If you have something like say a truss, got ugly. Sorry. All right, let's say you have a truss, and you have an anchor here and an anchor there. We found out early that if you have, say, a force here and a force there, that, and let's say you have another force here, that this is statically this is not statically determinate. This is what's called indeterminate. And the reason for that, and there's a little section in your book if you want to reread it, but it's a fairly simple concept. It just means that you have more unknowns than you have equations. And the reason you have that is because here at A and B, you have an AX and an AY, you have a BX and a BY. And so no matter what you do, you'll only ever be able to know that AX plus BX plus, let's say that force Q, plus Q equals 0. But nothing you can do will allow you to calculate these, right? Because it's statically indeterminate. So I showed you how we put rollers on one. That eliminates the BX. That's how you're allowed to solve for it, okay? So just an idea if it comes up. All right, so frames, machines, kind of part and parcel. I would, for frames, for machines, I would look back on the toggle clamp. All right, that's a good example. It shows the way that we use two force. So it forces you to identify two force members. All right, this is important. So whenever you're solving for the toggle clamp part or the clamps, the ones on the homework number 8, always had the two force members, and that's the only saving grace you have, because if you don't recognize it, you end up with too many unknowns. You go for circles, and it's very frustrating. All right, so look at that. As far as machines go, they're variation, but again, you might be asked to find a single member. So maybe you have kind of like the homework, you have something that looks like this, and then there's maybe another member that goes down like this, and maybe it's anchored here or something. So this is one member here. So you may have to dissect it. So just look back on the examples that I talked about for frames, and you should be fine. All right, and then our last, in probably the one we haven't talked about as much, is friction. So no wedges, no belts. So that equation, T2 equals T1 e to the beta times mu, will be on the test. All right, so don't sweat that. It's an easy topic, but we could easily combine that with another problem. We're not doing it. It's too much. So as far as friction goes, keeping it simple, if you imagine you have a block on the ground, you apply a load to it, and there's many variations of this type of problem, right? You could say, minimum mu to move, right? Or to not move. So you could give the P, you could give the weight, or you could given mu equals 0.35, find P to move right. Or you could have additional force, and then say maybe have 1,000 newtons going this way, find P to stay put. So really these problems are all really just using the idea that if it's on impending motion, then that friction force is mu static times n. And since friction force is generally in the x direction and normal force is generally in the y direction, this gives you a way to substitute so that you can, using some of the forces in the x, some of the forces in the y, allows you to get rid of an unknown in one of those and solve. All right. So that's it. Piece of cake. All right. So no, I'm not trivializing it. I wouldn't kill yourselves studying for it. I would suggest, and again, it really depends on how comfortable you are with the material, but I would recommend that at a minimum you go through your notes, look at each, be familiar with each of the chapters. I've tried to highlight what will be on it the best I can without really giving you the exam, but you know, I don't. Everything we're going to give you is going to be a pretty much like a homework problem, but like probably a mainstream, not difficult. So if we give you a truss, it's not going to have some gnarly geometry on it. It's not going to be like the one that was like a upside down roof. We're not going to try to trick you with some weird things. It's going to be very simple. If we give you a friction problem, it's going to be just a block. It's not going to be some crazy system. So again, we're just looking to make sure to satisfy my knowledge that you understand the material and you're ready for the next step. Okay, I'll open it to questions now.
I had a question.
Yes.
So you know how in the midterm you told us like what certain joints could support like a lateral load? Are you going to tell us that on the final, or do we have to like memorize the reactions?
No, absolutely do not memorize the reactions. What I would do is, do you remember that I posted that table of reactions?
Yeah.
Yeah, and as far as, I think what you're referring to is if you have a thrust bearing versus a slider bearing, was that
right?
Fair assessment? Yes, you do not need to, I would tell you that. So because you can't really know, like if you have a door with a hinge on it, just from looking at it, you're not going to know whether there's a reaction in the plane of that motion, right? In that direction. So no, we don't expect you to memorize that. And there won't, I don't believe there's any reaction type questions on part one, and on part two, if it is something that you're not sure about, you can ask me.
Is this going to be, oh, sorry. Is this going to be open note?
Yeah, I mean, it is. I mean, because I could say it's closed note, but you guys have notes there. So I don't think, you know, the only people it affects are the honest ones, right? And I mean, I'd like to think everyone's honest, but I'm not an idiot. So I know that, you know, you're going to peek your notes occasionally. And in reality, I'm not a real fan of, you know, putting you in a room and seeing what you memorize, because that's not how you work in the real world. I mean, I've had to do stuff in my career where if I didn't have my notes available, it'd have been very difficult to do it. So that said, yes, you can have your notes. Just no live people. So no statics instructors on speakerphone.
Okay, awesome. Thank you.
All right. What else?
You mentioned we can turn in an Excel. Does that mean we can turn in 2 files in the when we submit the quiz or the final?
Yes, that is correct. So yeah, if you choose to do frames and machines with Excel, then you would just submit your midterm, obviously, with the problems, and then on your midterm you could just write. So I think the way I want to see the midterm, and I'll reiterate this on the day of the test, but you'll download you'll download it, and then you can either choose to print it like the midterm, where it'll have the problem. It'll have something like, number one, there'll be the question, and then there'll be the diagram you'll need, and then so you can either then write it all out here and then scan it, or you can write on a separate piece of paper. And so I know it's a test, so I don't expect you to, if you do it on a separate piece of paper, you do not need to spend time rewriting a nice pretty picture of what I showed you, but you do need to draw the free body diagram as appropriate. So that's what I want you to focus your energy on. So make sure the free body diagram is there. Okay. But yeah, if you're if you do have an Excel problem, just write C file and I'll see it. I mean, if you turn in 2 files, I'll assume that's got to be, because that's really the only problem you can do with that. All right. Okay, what else?
So we're meeting on Zoom on Monday to take the synchronous part, but the asynchronous is at any time Monday.
That's correct.
Okay.
Could I see the slide with the part 1 details again? I showed up a little bit late. I had some internet issues.
Oh yeah, let me share it again for you guys. I'm also recording this too, so it'll be a bestseller. There you go.
Mhm.
There you go. That's part 1. So again, you have
Right.
9 to 5 to do it. 60 minutes. No partial credits. Only downside, it'd take me
Yeah.
forever to go back through all those and figure out. And so you don't have to show any work either. So you won't turn anything in with that. Unlike the quiz where you submit the work at the end, with this, you'll just take it, put your answers in, submit it, you're done. And
Yeah.
typically it takes, I've noticed most people take about half an hour to do it, but we give you 60 minutes.
Mm-hmm. Why the split up, by the way? That it just seems like a very strange setup you got.
Well, we decided this. This was what we decided when COVID hit last spring. And traditionally, what we would do is we'd give you a 3-hour test with 5 midterm type problems. And we thought that this might be better because I think taking a 3-hour test of 5 really fairly difficult statics problems is pretty stressful. And we found that this part allowed us a little more flexibility. So I think the overall I've seen results and grades have improved by it. But in the fall, I don't know if we'll continue this or not. It's hard to say.
Well, next fall we'll be taking dynamics, so
Yeah, I hope so. I hope to not. I mean, as much as I like you guys, I don't want you to see you again. Not in statics, I don't. So
yeah. I've heard dynamics is pretty tough compared to a bunch of other classes. Like it
is hard. I mean, it takes more time. I think the challenge with dynamics is there's just a lot more. Each problem can be so much different, even within the same chapter. I mean, you probably noticed, like, if I give you a truss, it's pretty much solved the same way. I mean, the geometry might be hard, but there's kind of a formula that I've shown you how to solve these. But dynamics, I don't know. The dynamics, they really love pulleys, and they love accelerating pulleys, and I never quite figured that out in I may teach dynamics one day. I don't know when, probably maybe the year after next. But it's the whole idea is if you have, a pulley, I can't see this, but you have a pulley and then you have another object. Oh,
You're not highlighting your video.
yeah, I realized that's probably better. I wasn't not drawing, but let me go ahead and there. So what I was saying is that, you have these pulley problems where you have this object here, and then maybe it goes there, and then goes. No, I'm doing a poor job of making them up, but they'll have. Maybe have this connected to. Yeah, forget it. Anyway, point is that I'm not doing good drawing on the fly here, but the point is that you'll have like a mass here and a mass here, M1, M2, and you'll have to figure out, this one goes up, that one goes down, and then you'll set everything equal to MA for the system, and you'll figure out what A is for the, since the blocks are connected, and then you have to use the proportions of these. Anyway, I don't want to get diverged, but so statics wise, any other questions or anything?
I had
Okay.
a quick,
Yeah, sure.
just on zero force members. So there's the one where you have there's 2 kinds, right? There's one where you have the like 2 members going together at straight and then one coming off, and that one's a zero force member. What was the other kind?
So yeah, so what you described would be something like this.
It was very technical, but yeah.
That's okay, yeah. But so basically if you have 3 members coming together and 2 are collinear in a straight line, then the third is a zero force. And so you usually see that in trusses where they look like this, or there's one member coming down, right? And so that's a zero force, even though this would be. So the other kind would be if you have 2 coming together And usually we have this here, so that's not the case. But if there's no support or no force, then these two would both be zero force.
Oh, okay. So just two coming together, and they're not linear then.
That's right, because they can't support loads in different directions.
Yeah.
So yeah, there's really, I mean, just remember that if it's zero force, it doesn't matter like what's going on up here. Like if I move the support there and get rid of this support, then even though you have, let's say you have even a load there, 1, 2, 3, 4 plus a load, and it doesn't look like it when you come down here, the fact that it meets the criteria means that it's not doing anything. And if you were to go up here and try to solve, you would, well, for one, you have too many unknowns, so you wouldn't. So you'd get flustered and say, what's going on? But I mean, like if I had done this problem like a real problem, then I would have started here. I would have solved for this and this, right? And then coming up to here, this would have been 0, and then I would have just had 2 unknowns. So I could have then summed the force in the x, summed the force in the y, made 2 equations, 2 unknowns, and then got this and this. So, but hopefully, I don't think, if it thrusts, I don't know if we're going to have you be that complicated. So, never know. All right, what else?
I was wondering, for the moment of inertia equation for a semicircle, is the 0.1097 r to the fourth like the equation we're supposed to use, like always?
No. So the way that works is if you have, because your book just gives you this, right? And so what this says is that if you're taking the moment inertia from that, it's pi over 8 r to the fourth. If you're taking it from here, then that's 0.11 r to the fourth. So remember that anytime you have this shape and you're using the parallax theorem. So if you have kind of like the inverted problem, had that upside down part here, but I mean, you could even have it like this where you had a triangle on top and then that there too. And so if I would say find the moment of inertia, about like the centroid, let's say the centroid's here, right? I'm trying to find Ix, and I know that this is y bar. Then of course I would find, the centroid of this piece here, and so this would be my d distance. I'd find the centroid of that. That would be d2, and then this would go from here up to here, and that would be d3. And because I'm going to the centroid, then I do 0.11 r to the fourth plus a d squared. And this would be triangle 1 over 36 base times height cubed plus a d 2 squared. This is 3 squared. And then of course 1/12. I'm sorry, 1/12 bh cubed plus ad 1 squared. Okay? And that's how you set them all up. So just remember, it's just with the parallax theorem.
So technically, if your centroid or going from the widest diameter to your centroid is the opposite direction of going from the biggest diameter of your circle to the centroid of the whole thing, if you don't pass it to centroid of the semicircle, don't you not have to do? You can take it from the diameter. I don't know if that was.
I don't know if I understand your question. If you have a composite structure, and I guess it depends on the orientation too. So, for example, if
sorry, could
Sure.
I think I can explain it better.
Sure.
Like in your setup here, if you go from that widest diameter down to y bar, that
From
you
here
don't. Yeah, you don't pass the centroid, so can't you use AD squared from the widest diameter?
Right. No, you can't. And that is a common question, is it? Because it seems like, well, why not? I mean, if you either go from there to there, there to there. And in some cases it will work okay. So for example, a lot of times if you say, because from the base of a rectangle, it's 1/3 bh cubed. And from the center, it's 1/12. So in this problem here, if I went from here up to my centroid, wherever it was, after I made my little shape, then it may work to go from the base and use 1/3, but more often than not, it doesn't work. So what we do is we just teach you that whenever you have a composite structure, always go make your D distance to the centroid of the composite shape and use the composite shape's centroid or its moment of inertia about its centroid equation.
Right.
So yeah, you can roll the dice and it might work sometimes.
Well, it won't work every time that you're going away from that object's centroid to go to Y bar.
You know, that's a good question. I don't know. I haven't tried enough permutations of it. I haven't actually derived the equation, the parallaxis myself, so I don't know. I mean,
Because I'm thinking is, or because when you the reason you go back to the centroid is because if you were to go from the, if you're going to pass its own centroid, the moment of inertia would get smaller and then it would start to get bigger as you moved away. But it would always
Yeah.
get bigger if you.
Right. That does make sense. I mean, I understand the logic of your thinking and you might be correct. I just don't know. I don't know. I haven't studied that closely. Okay. Any other questions?
Are we gonna have to like? There was like that weird homework problem where we had to like look up a chart for like an I-beam or something. Do we have to do that on the exam?
No. You wouldn't have anything. No weird stuff like that. So,
Okay.
as I said, if you get the moment of inertia, if that does end up being a question, then you'd have something, like I said, you'd have a simple shape. You'd probably end up making 3 pieces out of it, find X and Y bar, and then find either the moment of inertia about the X or the Y. And that's pretty much it.
Okay, thank you.
Sure. Anything else? All right.
Is part 1 just going to be a Canvas multiple choice? Because you said we're not submitting anything, right?
Correct. So that's what you'll have.
I had one more question.
Sure.
Could you go over like, remember when we had like for the moment of inertia, we had to do, there was like problems with density in it, and then there was like problems without density, and there's like a different way you had to go about it.
Right. So you very doubtful you'll see that, but just real quickly, just so that you understand it. If you're dealing with density, it's usually obviously if it's either areal density, linear density, or volume density. So they're all solved the same. So volume's most common. So what you would do is you would say, if you had like, let's just say something simple like this and that, and then maybe a triangle over here. And we'll say it's a triangle like a rocket ship. So anyway, but let's say that you say that this has a density rho of say 5, and this has a rho of 3. This has a row of 3, and this has a row of 4, and more complicated you ever see. But all you would do is you would say you'd find for the area, you'd say what is the area? You have 1, 2, 3, 4. You'd find the area of each, and then you'd multiply that area by the areal density, right? So for, let's say, kilograms per meter squared, or whatever the unit is. And then you'd find, this would just be your mass. And then so what you do is by multiplying this by this, then you get a mass. And then you'd have your X bar, Y bar, and then you have X bar M, Y bar M, and sum M. So then X bar would just be equal to the sum of the X bar M's over the sum of the M's. That's all. So you're just basically taking either area, line length, or volume, and multiplying by density, and then that compensates for the fact that this has less density than mass. That makes sense.
Yeah, but so is it always mass that we're doing then?
Well, yeah, because it's center of mass at that point, right? Because if it has different densities, then it's center of mass. That's the only reason why you would treat these differently, is if they had different masses, because of the way you have those.
If density was just volume, then you could just go off of like volume.
Yes. So yeah. So if this was V, then you just multiply by that, you get your volume. But it would still be mass, right? So it doesn't matter what this is. It'll just always be mass, and you're always finding that. All right. Okay. Any other?
Sorry, I had another quick
Oh,
question.
sure. Sure.
Do we need to have the centroid equations up? Or-
I mean, you should have them. I mean, they're in your book. You can look them up, but I would know. I mean, I would know them. Have them for a triangle, a circle, and a rectangle, and that's pretty much it. I mean,
oh, okay, yeah, that's pretty.
yeah, we're not gonna ask some crazy shape.
No, like weird semi-ellipses and.
No, because that doesn't. At that point, we're not really testing your like, statics knowledge. We're testing if you could do this problem. So no, we're not like that. All right. Anything else? Okay. Well, thank you guys for coming. I do appreciate it. I was hoping. I'm sorry the short notice. I had no idea until this morning what time I was going to be able to do it at. So yesterday would not have worked, but I'm glad you guys took the time to do this. I think it'll be beneficial for you. So I will see you guys on Monday night. Email me during the day on Monday. If I can't get back to you, I'll do my best too. Otherwise, good luck on the test. You guys will do fine, and good luck on your other finals. All right. Take care.
Thank you.
Thank you, Professor.